Well, good afternoon to you all. So my name is Sandrine THUILLIER. So I'm a full professor in mechanical engineering at Université Bretagne Sud, which in the west part of France, in Brittany. And my talk today is related to from homogeneous to heterogeneous mechanical testing of metallic materials. And I will first first of all, what I would like to do is very rapidly introduce my research activities that I will define with three scientific keywords. And the first scientific keyword is virtual forming, because I'm interested by the influence of the mechanical behavior of the material on forming and joining processes by comparing finite element simulation with experiments. So here in the cup of here in the example of cylindrical cups, one or two steps, twisting of very thin copper or steel sheets, and here in the case of hemming. So always this comparison between numerical simulation and experiments. And to do this, we need material model and we need to calibrate the material model. So my second keyword is calibration of mechanical model. And it is finding the material parameters, the ones used as input to a finite element model. And when dealing with a mechanical model, you need information and to obtain this information, you do mechanical testing. And here is my third keyword, which is mechanical testing. And since several decades, I've been torturing materials by pulling, shearing, bulging them, and even worse, cutting holes, and to derive this very precious information on their mechanical behavior. And although I've been working also with elastomers and polymers, my main focus is metallic materials, aluminum, steels, titanium, and copper. And my talk today will be focused on metallic materials. I've been working since quite a long time on the influence of the mechanical behavior of materials, on forming and joining. And as you know, mechanical models become more and more complex and with a lot of parameters and taking account of more and more phenomena, even at the macroscopic scale. And my talk is mainly dedicated to phenomenological models. And we need more and more mechanical tests. And what you have in mind is for one deformation mode, you need one homogeneous mechanical test. So nowadays, when I start a new project and, characterizing new materials, we make a list of all the mechanical tests that we have to perform in order to characterize the mechanical behavior. And this list is longer and longer. So in order to characterize anisotropy, hardening, and rupture. So the aim is, how can we deal with such a huge amount of information? And I will start with a question for you. So what is your absolute dream? And okay, in the field of mechanical testing, of course. Well, mine is, I would like to have such an input. And this input is to have the equivalent stress as a function of the equivalent strain for a given material. And you have really a perfect, a unique curve that will describe the mechanical behavior of the material. Of course, you know that to derive such a curve, you will need a model in order to have everything superimposed, whatever the orientation, for example, of the tensile test. And this dream, well, in order to reach it, you need several mechanical tests. And I think we are not that far. And here is from literature an example of this, the flow stress as a function of the true plastic strain. And well, it's not one curve, but we are coming more and more. But in order to have this, well, you have all these tests to characterize the mechanical behavior. So mechanical testing is a key to reach my dream. And as you know, mechanical testing will give you the answer. And when you consider a sheet metal, you mainly define the deformation, the strain, well, deformation mode, or the stress state in the sheet plane. And here you've got the minor strain, and here on the y-axis, the major strain, and one straight line is one mechanical test. So you've got biaxial testing, simple shear, tension here, and tension with necking, so it's not really a linear strain path. And for each curve, you need a mechanical test. You have a similar representation in the stress space, so using the component of the stress tensor. But for reaching such an information, you need some information. And from this, you may have two different trends. One is I call big database. So for one material, if you want to characterize in tension, in shear, in hydraulic bulge test, in plane strain tension, up to rupture, you may have to do, and this is my own calculations, around 60 quasi-homogeneous tests, and maybe up to 100 if you consider to include reverse strain path change. So it's a lot of time, it's a lot of material, it's you need human resources in order to carry this out. So one solution is to do automatized testing, and you may be aware, for example, in Switzerland by ETH Zurich, they have developed mainly for tensile test, automatized mechanical testing. So this is what I call big database. And I will suggest another possibility, which is what I call smart database, which is well, less data, so less mechanical testing, but in order to reach the same amount of information, you will have to use heterogeneous tests, meaning that with one or at least a few tests, you will obtain an information as rich as with several homogeneous tests. The main question is, well, what kind of test can I do? And this will be the aim of my talk today. After this introduction, I will briefly review from the state of the art what are the, well, a little bit of history of heterogeneous tests, and then some ideas on how to choose heterogeneous tests, and then I will conclude. So dealing about heterogeneous tests, it seems to be understood that one of the earliest one, okay, is in 1998 by Mevisen, but maybe the very, very first one, and you recognize this is tensile test, a very classical one, but beyond necking. And when you are beyond necking, well, this is obviously something which is non-homogeneous. But the problem with necking is that it's an uncontrolled mechanism. You never know exactly where necking will occur, so you don't control the heterogeneity, and it could be a little bit difficult to follow by digital image correlation. So the idea was to use discontinuity in order to control where the heterogeneities will occur in a sample. And so the idea is to add holes, notches, to promote shear-like tensile zone. The main issue, I would say, is that there is no standardization for this heterogeneous test, which means that there is a large number of them. And well, here is maybe the first one, 1998, but you can see it has been a kind of ongoing activity, and we still have new tests together. So what these authors have introduced is mainly notches on tensile test. So here you've got monotonic loading. So you just pull in one direction. All of these geometries, you just pull along one direction. Tensile type heterogeneous testing. But you can also have holes holes and also discontinuities. The idea is to have a rich information where you have materials, of course, in order to replace several tensile shear tests by only one test. And many more again. So usually people have designed these geometries by intuition. This is typical engineering by intuition. So they try to guess what could be the good geometry in order to obtain a rich information. And we know if we add holes, it will promote localization, but near the edges, it could promote a kind of tensile test. So this is the main ideas. And there's also a different approach, which is using optimization. You could, by shape optimization, obtain geometry. So you take an indicator and you try to maximize the heterogeneity. So, for example, the strain range, you want to have both small and large strain during your test. So you try to promote a large range of strains, but also strain paths. So by defining these several indicators, you may end up by having a geometry, so by shape optimization. And I would say more recently, people have also tried topology optimization in order to design a good shape. So this was the very first one, and you can see even in 2021, and I would say it does not stop there. Even nowadays, there are still more geometries. In this case, these are biaxial testing. So you can also reach, because having a biaxial state is very important in sheet metal forming. So people have thought about several geometries. You can see the ideas is always holes or special geometries in order to introduce biaxial testing, but also here shear, and also this, which is both shear and tension. And if we have already mentioned that people design this shape not only by intuition, but also by topology optimization. You know, by topology optimization, you put materials where you need it, so you will create holes. Necessarily, you have holes within your sample. So these are different methods in order to design a heterogeneous test. And the previous one were mainly in plane displacements, but also you can find some out of plane test. And I will say this one seems to be typically inspired by the forming process. So you've got a circular blank and tools like in forming. And by moving this tool in this direction, you will have mechanical deformation, and it is out of plane displacement. In this case, they use incremental sheet forming, directly the forming test, in order to identify the material parameter. So you see a wide range of heterogeneous testing. And I would say in literature, every study has its own, every article more or less has a different heterogeneous test. Okay, so now you've got a shape. If you find out how to choose one, so you've got a geometry, boundary conditions, and we can define what we call the 3 pillars of using heterogeneous test, which is you need inverse identification. In this case, you don't have a direct closed form analytical expression relating strain, load to the stress and strain. So you will need finite element analysis and inverse methodology in order to determine the material parameters from the output of your test. So classically, I would say that nowadays there are mainly 2 methods. It's not the only ones, but I would say that these 2 ones are rather the most used one. So finite element model updating, FAMU, and VFM, virtual field methods. In these two cases, this is inverse identification. And in the first one, you will use, I would say this one is the most straightforward one. You use a finite element model. So let's imagine you've got here on the top, this is the numerical model, finite element model, and at the bottom, this is the real experiments. So you create a finite element model, you simulate your test, and using an optimizer, you will minimize the difference between the output of the test from the numerical part and from the experiments, and by decreasing the gap in between, you will reach a parameter set. So this is a finite element model updating, and maybe I did not stress enough the fact that you need a local strain measure for your experiments. So using digital image correlation in order to capture the whole strain field. So you've got this material testing with DIC, you've got your model, so mechanical model, and with the inverse methodology, let's say FAMU, then with these three methods, you will be able to determine the best, or at least a very good material parameter. So we can see this procedure as a multiplicative system, meaning that each pillar should be well controlled, and the quality of the experiments and the quality of your DIC measure, the capability of your mechanical model to reproduce the mechanical behaviors material, and the convergence of your inverse methodology, each of the pillar is very important in order to reach a successful outcome. So I will now focus on some example in order to show you what kind of results can be obtained. So my first example is about biaxial testing. So in this case, it was performed with both aluminum alloy and a DP dual phase steel. So this cross-shaped will lead to a non-homogeneous strain field in the center here. And just to give you an idea, in this case, so we used digital image correlation to capture the strain field, but we didn't use the whole information over the, so the area of interest is all this, but we used only information along a line in order, I would say, to simplify the problem. And if you follow this information, if you have a look here in the minor strain and major strain graph, you can see that, for example, in blue, this is for aluminum alloy. You do have points along a line which is very close to uniaxial tension. You've got points close to biaxial tension, but you've got also points, several orientations. So meaning with only one test, you can cover all these kind of homogeneous state. And this is the richness. So for aluminum, we reach higher strain. For dual phase in red, strains were lower, but more or less these are the same strain paths. So meaning that with only one test, you can cover more or less 1, 2, 3, 4, and 5 strain states, and you would have needed 5 different mechanical tests in order to reach the same thing. So this is really the illustration of the interest of heterogeneous testing. And so what was done, it was to calibrate by inverse methodology a mechanical model. So it was in this case, well, isotropic hardening with an isotropic, so Bron and Besson. I know it may be not familiar to you. It's a French anisotropic yield criterion involving 12 parameters. So we used such a criterion. The model was calibrated from one cross-shaped specimen in biaxial loading, and then we performed numerical simulation of tensile, a shear test, and a hydraulic bulge test, and compared with experiments. And so you've got in the thicker line is for the experiment and the thinner one for the numerical simulation. And you can see that the agreement is quite good. So one test and you can reach a very good correlation with the prediction under monotonic loading. Sorry, not really monotonic, a homogeneous type test. Okay, so this was very encouraging results. So let's try to go on. One of maybe the challenge is that it will depend on the material. And in this case, so it's a purely numerical study. And okay, this is only 1/4 of the sample. So imagine you've got a biaxial loading. So you pull along that direction, you pull along this one too. And this is just 1/4 of your sample. And in this first line, this is for a steel. And in this second line, this is for an aluminum alloy. So it's purely numerical, but the material parameters were taken from a real material. And what you can see is that you don't have exactly the same strain field for a given displacement. And for example, in the case of aluminum, you have quite a large localization of the strain in this area that you don't have in the case of the steel. And the consequence is that if you have a look in the strain state, you can see the points are not exactly located at the same place for the steel and for the aluminum. And this is the same representation, but in the stress space, meaning that your test will be sensitive to your material. So if you design your test, your heterogeneous test, considering only one material, you may be surprised if you change your material that you don't have exactly the same information, because you realize here you don't have the same strain state that you can have here. So that's a challenge with heterogeneous tests, and you have to investigate the influence of the material behavior. Another example that I've maybe already a little bit mentioned previously is this shape was designed by shape optimization. So we used an indicator in order to promote several features in order to enhance heterogeneity, to enhance several strain modes over the sample. And the funny shape that you have here comes from this shape optimization. So this is numerical simulation. This is a real experiments. And you have, again, a comparison of several tests. We perform the test in shear, tension, and hydraulic bulging, but we also did the simulation with the parameters identified from this test, and you have really a good agreement. In this case, it was also hardening and anisotropy. It's just to illustrate it's a different shape, but it can give you still good answer. Now, back from the literature, people have also used this approach to calibrate Johnson-Cook's model. I guess you know Johnson-Cook's will give you a dependence on in this case, it's not temperature, but it's mainly a dependence on the strain rate sensitivity. And so they use Johnson-Cook, and to calibrate, you will need several tests at different strain rate. And in this case, so you've got here the quasi-static test, and this one in the dynamic test. And they considered two heterogeneous tests, one in quasi-static condition, one in dynamic loading. And they succeeded to calibrate Johnson-Cook's model with only these two tests compared to 5 with homogeneous tests. So the idea, what it is, it's because you have a strain distribution, but you also have a strain rate distribution within a single test. And using this strain rate distribution over the sample, you are able to calibrate, for example, Johnson-Cook, just for this given test. Of course, here you've got just an illustration because there are some limitations coming from the experiments. Because in case of quasi-static loading, you used cameras which are different than in the dynamic test, because you need high-speed cameras in case of dynamic testing, and you don't have exactly the same resolution, and you don't have exactly the same information. What can be illustrated is you've got more information during quasi-static loading compared to dynamic. So there are limitations, of course, related to the experiments, and it refers to what I mentioned previously. The quality of your measure is very important within this approach. Well, it's just another illustration. And in this case, the range is the strain rate. So you've got here an illustration of the range of strain rate of the sample during one test. And my last example in this part is now mixing strain rate dependency and temperature. So in this case, we used a heterogeneous test in temperature, and a global simulator was used. So a global, you have electrical currents going through the sample. So here is your sample, so in tension, and you've got electrical current going through the sample, and you regulate the intensity on the temperature that you want to reach. For example, here in the center, you've got thermocouples at this free position, and you regulate your test on the temperature in the center. And infrared camera was also used in order to capture the full temperature field. So you have an idea of what is the temperature field over the x coordinate, which is the coordinate along this direction. So you've got both, in this case, a localization of the strain in the center, but also a temperature field, which is non-homogeneous. And the idea was also to calibrate a Johnson-Cook's model, but both considering, it's a multiplicative model. So you've got a hardening test multiplied by the strain rate dependency multiplied by the temperature dependency. So the idea was to try to identify all the components. In this case, the virtual field method was used, which is another method in order to calibrate by inverse methodology the material parameters. And so the load signal was used at 3 different speed of the test, and the idea was to investigate and to characterize the strain rate evolution. So over a sample, you've got an evolution of the strain rate, and this information will help you to calibrate the model. So here is typical results. So you can see, well, in this case, quite a good description of the load. Well, it's not that good at this strain rate, but we also know it comes from the limitation of the Johnson-Cook model. So this was my main, I made a kind of selection of some typical results in order to, well, try to get you convinced of the interest of heterogeneous tests. So my next question is, are you ready to come on board? Okay, on board of the train of what we call the MT 2.0. So the name comes from Professor Pierron. He wrote a paper in Strain, and he calls this approach material testing 2.0 or MT 2.0, which is, well, the new way maybe to characterize mechanical behavior of the material. But if you're interested by MT 2.0, the next question could be how to choose a heterogeneous test. I've shown you there's quite a lot of geometries, so how to choose one. So I will just try to illustrate a little bit how we can do this. So just to show you, in this case, we consider, so several geometries are considered. So always heterogeneous test. So you have got here the full geometry. So biaxial loading, uniaxial loading on a notch specimen, also uniaxial loading on what we call a D shape. And here, uniaxial loading in this direction on a sigma shape. So 4 different geometries, which one is the best one? That's more or less the question. So in this case, we need indicators in order to characterize the mechanical state, because the idea is that we want a rich mechanical state. So how can we define indicators? So indicators, you've got here a distribution. So I forgot to mention, in this case, it's a numerical study. So what you can see here are the results of the finite element simulation, considering 3 different materials: a pure copper sheet, an aluminum sheet, and DP600 material. Although it's virtual, real material were considered, and so material parameters comes from real material. So the idea was, beware, as I mentioned previously, as localization may depend on the material, it's interesting to investigate several materials at the same time. So you've got here a distribution. So for the 4 geometries, 1 material, this is aluminum and this is steel. So you've got here the equivalent plastic strain, but you can also plot several other information, like you are here in the major strain, minor strain, so you can try to compare the test. Do the same for the major stress and minor stress. So this gives you information, and you can also, in this case, this is what we call the rotation angle, and the idea is how the test is, how the information in the test is oriented compared to the rolling direction. So it can give you if the test is mainly centered in the rolling direction, so in this case it's 0, or if you have a better distribution, and in this case you can see that you have something more distributed, so maybe you will be more able to characterize an anisotropy with such a test compared to this one. So from this material information, you can build indicator, and for example, this is a strain-based global indicator. So the idea is to gather the information in one scalar parameter, information on the number of strain states. We want to promote a large strain heterogeneity in order to reach both small and high strain, and to have also some maximum strain for selected, well, like selected strain state like tension or shear, etc. And the idea is to define using what we call diversity of the mechanical information. So I will not, well, go too much in details about the equations, but these are quantities, and the aim of these quantities is to represent these ideas. So that if you look at here you've got the what we call the strain ratio, so the minor strain over the major strain, and you count the number of elements in your numerical model. And if you have a distribution like this, I would say your test is very good for heterogeneity, but if it is all centered, this is a kind of a homogeneous test. So the idea is to promote this behavior and not this one in order to have a rich information. So this is the idea of this indicator. So here are the, it is additively built, several component contributions, and of course you've got weights. And these weights, well, the influence of the weights was a little bit investigated, but maybe not deep enough. And the weight is in order to promote, well, the influence of one contribution compared to the other. And what was performed was a comparison of several heterogeneous tests. So you've got here shear, uniaxial, biaxial. I've shown you this one, which is kind of forming type, bulge, plane strain. You see all these tests that we can know. We can rank them using this global indicator. And the idea was, well, we know the test, we know all of them, more or less, and which one is the best one? And maybe we know that this one, for example, seems to be quite complex, and biaxial is still a good one. So in this ranking, well, we can see that biaxial is maybe one of the best. So this is the idea: define indicator in order to rank and then to help you to choose what is the best test. The idea of the global indicator was modified a little bit, and in the case of a research center in France, they use a kind of stress and strain based indicator, and also using the principal virtual work, which give you, you know, when you do finite element simulation, you want to minimize, you use the principal virtual work, and you want to minimize this difference. So they use this information in order to build the indicator. So just to highlight that there are several trends in order to characterize the heterogeneous test. And in this case, we consider 4 heterogeneous tests and 2 different indicators, either stress and strain based or based on the principal virtual work. And the idea is, can we compare these 4 tests using either this indicator or this one? And I remind you, the idea is still which one could be the best one. And here are the results that these authors obtained, so still in this research center. And so, okay, lots of information, but the idea is that each information here is for one test. So this is a notch one, sigma shape, D shape, and the optimized shape, okay? And they compared for the different colors. So let's maybe focus on one test. So they calculate the indicator. This one is the indicator based on strain and stress. And they compare different configuration, and especially what is the influence of the quality of the strain measure. So either you consider DIC without any noise, this is numerical simulation, but it was also possible to introduce some noise in the DIC. And what is the influence of the noise on your calculation? And what they've shown is that you have to be very careful, because you may have an influence, a non-negligible influence of this noise on your results. So this has to be taken into account when you consider heterogeneous testing. And one way is, because as maybe I've shown you, at the moment, the design of the heterogeneous test is mainly from numerical simulation. And one possibility to take into account the quality of the strain measure is to use synthetic images. So you can generate synthetic images, and you can put noise in your synthetic images, so that even if you remain within a virtual world, you will introduce some variation coming from the noise of your DIC, a virtual DIC. And so this is very important. And next, I will also show you some other results. And I simply wanted to mention that the other results were obtained within a European project, still going on. It will finish by the end of the day, led by a colleague of mine at the University of Aveiro in Portugal, and several partners in Italy, Belgium, also Belgium, and Machidi, which is a provider, maybe you know them, is a provider of a DIC system and they also provide solutions for synthetic images. So within this project dedicated to heterogeneous testing, we've performed still a comparison of several tests and using a different indicator based on a multiplicative form in order to rank the test. And I simply wanted to show you, sorry, a bit too rapid. So this is tension on notch. This is shape optimization, well, sigma D, and this is the topology optimization sample. So this is purely numerical simulation. And you can see that, well, it seems to this test, this is the value of the indicator. It seems to be a good solution. So we did an experiment, and here we are at the moment, because I would say that in heterogeneous testing, there's been a lot of work in numerical simulation in order to find the best geometry. But at this stage, there are less maybe results in the experimental part, and the main aim, I would say, this following months or year is to obtain also experiments. And you've got an example here of this topology optimization sample. So it's here more or less in the initial stage, and after deformation you have, and it illustrates very nicely where you do have localization of the strain, but you also have a huge amount of information coming all over the sample. And well, time for my conclusion. So, well, I would say I've tried to summarize my conclusion in 3 main parts. So I try to promote smart databases of heterogeneous tests. So because you still need to carry out a lot of tests, and you need to evaluate the robustness of your heterogeneous test. So you still have to perform on several materials and try to design indicators to carry out this evaluation of the comparisons. And yeah, this is mainly my main conclusion. And I just highlight here a few perspectives that we try to go on. Okay, so more experiment, as I mentioned, on heterogeneous testing. We try to promote, again, a benchmark, performing the same test in several labs in order to compare. And this is one of the aims of the European project I already mentioned. And also, if we consider calibration from homogeneous or from heterogeneous, what would be the influence on virtual forming? Because the aim of calibration is to be input data from virtual forming. And well, maybe finally to introduce strain path changes, because I've presented mainly uniquely monotonic loading. And here is it. This is just very rapidly my co-authors that work with me on this topic. So several past and ongoing PhD students as well as master's students. And very, very finally, thank you very much, Jan, for your very kind invitation to be with you today. And also, well, thank you, all of you, for your attention.
Thank you so much for an excellent talk. Very, very detailed in terms of looking and also looking at the history as well as looking to the future. This is excellent. Thank you so much. You know, Glenn has his hands up already. Go ahead, Glenn.
No, I didn't really. I was just giving a little clappy thing.
Oh, clappy.
But I guess while you called me out, maybe I will ask a question. So how does kind of damage fit into this? I didn't quite understand all the, how all the pieces fit together. How does varied stress states and damage fit into the framework that you have there?
You mean if you want to calibrate a damage model, for example?
You want to calibrate a damage model, or how you bring that in? I mean, really, you're kind of, I think, trying to look sort of for universal effective stress, effective plastic stress, or effective plastic strain plastic strip model.
I would say at the moment it's mainly dealt with, uncoupled rupture criterion, for example. So it's not real damage, but it's mainly dedicated to hardening, okay, and anisotropy, and you can introduce uncoupled rupture criterion. But if you want to consider damage, it's still ongoing. But you do have coupled damage model. In this case, you also may have some specific geometry with rupture occurring at a given place in your specimen, but then it will stop, and then you will have a crack occurring at a different place. So you may need for damage to use different geometries. But the idea, up to now and up to what I know, there's no real identification from heterogeneous of damage, like GTN model, for example. I haven't seen results.
It would seem like this would be a powerful thing to do with it, because you have a wide variety of triaxiality through the sample. So
yeah, right. But at the same time, it's also, it's quite sometimes tricky to identify damage models. So.
Yeah, you need good experimental data. So you need
it's a challenge, I think. Yeah, but you're right.
Small angle neutron scattering or something to identify.
But I honestly, at the moment, it's more focused on designing the geometry and also to focus on anisotropy and hardening. That's right. First step,
That gives you the idea probably for the next proposal, Right,
maybe.
John, please.
Yeah.
John?
Thanks very much, Sandrine. I enjoyed very much listening to the various interesting sample geometries. My question, first of all, is just kind of a practical one. Some of them look rather complicated to machine or to make into those shapes. So could you comment on the sample preparation and how those are actually done to make sure that that doesn't influence the results, at least in the early stages of deformation? Or have you seen it doesn't matter so much?
Okay, so with with laser jet cutting or water jet cutting, even if the geometry seems to be quite complicated, it's not that much difficult to obtain them. But that's right, you need to measure them after they were prepared to be sure that your geometry that you use as the input in your finite element model is the right one. It's not a theoretical one. So you will have to measure at least a few of them and to check that your geometry is the right one, because you need your finite element model to be as accurate as possible. And I would say up to now, we don't measure everything, but we try to have some characteristic dimensions in order to check with a finite element model. But as I mentioned, I would say that the next stage is to obtain quite a lot of data with such geometries, because up to now, we are mainly in the virtual world. We are in the world where we virtual design the sample, and well, we don't have that many information in experiments, so still going on. But yeah, I think with laser jet cutting or water jet cutting, it's not that much difficult to design this, to cut and prepare this sample.
Thank you.
Yeah. Sandra, so I have two questions, if I may. Sure. Let me give the floor to Marisa first, who is my student, I believe. That's Marisa, right?
Yeah. Thank you for
Marisa, go ahead.
Your specimen geometries are actually really cool, and I was just wondering, can you comment on what you think would be the best way to approach now the geometry design when you're dealing with fiber-based, like polymer composites or even ceramic matrix composites? Because when I was doing biaxial testing of those specimens, as we tried to make the cruciform geometry more complex, that just in turn just made the specimen fail right at those complex regions versus getting the behavior that we want to observe.
Mm-hmm. Yeah, for sure. Okay, this is for, as I mentioned at the beginning, this is for metallic material. So in this case, we want to promote large strain. So obviously compared to ceramics, it's very different. But when you do this, you need to introduce a rupture criterion because you can't go as far as you want. You need to stop your test somewhere. So you need to use a rupture criterion in order to stop when your rupture is reached. So I don't have any advice now to tell you about other material, but if you want to use your a different type of material, the model that you use in your finite element analysis at the beginning, you need to have this rupture criterion in order to know when you will fail. So the designs that I've shown you, they are really, I would say, useful for metallic materials. So material which are able to reach very high strain without rupture, but not for brittle, more or less brittle material like ceramic.
Oh, thank you. So essentially when we design them, then we just have to look for the behavior before the actual failure initiates.
Oh, yeah, that's the trick. You need at least an idea of the mechanical behavior because you design in the virtual world, your geometry first, before using it.
Okay, thank you.
Sandra, the question I have is when you do the inverse, retraction of the material properties, I assume you will basically looking at the force, try to balance, match the force. So when the sample becomes very inhomogeneous now, then what is the chance of, you may have non-unique solutions, right? When you do the inverse analysis. And how would you handle that kind of, back material extraction particularly when you have lots of different strain states?
Oh, I think, there is non-uniqueness for sure. And but the way to deal, if you consider homogeneous testing, if you want to calibrate a mechanical model with, I would say, quite a lot of parameters. Let's imagine, you've got an isotropic hardening, including mixed hardening, for example, kinematic hardening, etc. You have a large number of parameters. Even if you consider homogeneous testing, you are not sure about uniqueness. So I think at this stage, it's more engineering type. So we always try to investigate. And so this is the same answer for heterogeneous testing. But what we try to do is always to investigate the influence of the starting point. So try to change, and you can change it kind of automatically, the material parameters. So you try to change them and see if you always go back to the solution. It's more a kind of practical approach. But yeah, I agree. I will not prove uniqueness. You're right.
Okay.
One way, but just one way is the idea of identifiability, because some parameters, they will not really influence mechanical behavior. So one trend is to calculate a sensitivity matrix in order to have an idea of what is the identifiability of each parameter, so that you can well, I would say disregard the material parameter which are which will not bring any information, so that it will help for the convergence of your inverse identification.
I like that point very much. So if I may just do the second question. So one of the assumptions in the approach right now is the material is homogeneous, right, in the sample. Right.
Sorry,
so material is homogeneous in the sample. So when we have the cases, for example, when we say additive manufacturing done, and then we roll it down, and your material becomes a little bit, unhomogeneous in that sense.
Mhm.
Do you have any idea how we should handle, what could be the heterogeneous test and, handle these kind of situation? Basically, you have variations of the material spatially.
Yeah, for sure. So well, I don't know. Obviously, I don't know yet. Okay, what was done is, for example, if you consider it's not additive manufacturing, but we considered welded specimen, so by friction stir welding, and so you have also a variation of the mechanical properties of the sample. So we were able to retrieve, but we made an assumption how the properties varied in one given direction. So if you have an idea of how they change, you can identify by areas the material behavior. But well, in additive manufacturing, you may have variation which are more rapid from one area to the other. So it means you will have several types. And what I don't know, because I mainly work with sheet metal, so less with additive manufacturing, is what will be your aim? Because do you want to retrieve material parameters for each area, or do you want to have a global material which will represent everything? Because underneath your question is, do you expect to retrieve at each material point the mechanical behavior? So to calibrate the material parameters at each material point?
That's probably a long discussion. We are, I think that's probably open question, open-ended question. So thank you so much. We really appreciate your talk, and sharing your thoughts with us. And I'm pretty sure if we have any questions, we will follow up.
Okay, I really thank you very much for inviting me, and well, for being there today. Really, thank you very much.